So what are different sorts of nonlinearity that we see in PLLs? Few of them just intuitively I discussed last time. I repeat it now. Okay. First of all, we have this pulse frequency detector. So this pulse frequency detector has two outputs, up and down. And this goes to charge pump. Okay, so this charge pump actually are constitutes two current sources, right? And then at the output, we will get a voltage, which is the control voltage of VCO. Now if you look, practically we use this up and down to control charge pump in this fashion. There are two switches, and these switches are controlled by up and down. So this was practically the filter. And this C2 we decided to choose enough less than C. For example, it can be 1/5 to 1/10 of C. Now these switches will be MOS switches, and these current sources also will be MOS current sources, as long as we are talking about an integrated technology. So now if I replace them by switch, so here I will have, for example, a PMOS transistor connected to source current source, and this side I will have an NMOS switch which is connected to the same current source. So when down is 1, I want to sink the current, so it will work. But when up is high, when down is high, it will work properly. But when up is high, it won't work. I want to switch on this. Therefore, I have to put an inverter here and then give up. Right? But now the problem is I'm creating a delay from down to up. Right? Therefore, these two won't have same phase performance. So there is a delay. And because of this delay, then effectively it is like that I'm creating some offset in the output voltage of this circuit, and also that actually happens and appears as ripple. I'll give you one example. Suppose it is in a steady state, everything is locked, so it's perfect. Now what will be the waveforms? Okay, so for example, this is one of them. Say up. Okay, so there is a delay, right? Therefore, when this signal we call it up bar. So upper doesn't appear exactly after up, so there will be some delay. So this is up bar with some delay. Now I have down signals. Considering down and up are perfectly matched, right? This is the ideal case. This happens in the steady state. The reason is because of the delay, inherent delay of pulse frequency detector, there will be narrow pulses. It is just like I have extended this narrow pulse. So this is actually a narrow pulse. I'm just expanding it. I'm showing it wider so that we would, because this will be more than delay of one inverter. Okay, so this is width of that narrow pulse. I call it TD. This is, what is this? This was the delay of pulse frequency detector when up goes high, down goes high, till the time both goes low. And this happens because when these two are high, then it goes to an AND gate, then it goes to reset, right? And then reset has its own delay, AND gate has its own delay, so this will create that delay. Now, delay of one inverter will be here. Therefore, practically we will have this type of waveform on upper and down. So now these are in fact control signal. Therefore, what will happen for control voltage? VCTL. So ideally we would expect both of them to be on simultaneously. Means that we should not expect any current to be given to this RC network. But practically now it is done. If you look at upper is high. Therefore this switch is off. Down is high. Therefore the second switch is on. Therefore now I have a sink current in this interval, which reduces control voltage. When upper is low, both our switches are on, therefore there is no current in the RC network, so voltage remains as it is. Now again here, at this point, when upper is low and down goes low, so now I have a source current, which returns the voltage back to original value, considering two current sources are exactly the same. Now see, this appears as a ripple on control voltage. So therefore, effectively, though we are sinking and sourcing some current, but for this duration there is a ripple. So this ripple is effectively is like some sort of distortion. I have some sort of change in control voltage, right? Therefore, frequency of VCO will change during this time. So this appears in some sort of change in the frequency of VCO. Effectively, we want the amplitude of this ripple to be very low, and effectively we want to avoid this variation of frequency. This creates nonlinearity. Now we will see what we should do. We should just make these two paths to have same delay. So there are different ways. For example, I can put two inverters here and make delay of two inverters to be equal to one inverter. Or I can put a dummy transmission gate and make the delay of that transmission gate to be equal to one inverter. Second choice is better, because if I go with two inverters, then effectively I have to increase delay of one inverter. Then effectively I am creating delay between up and upper. So it's better to go with just a dummy switch here. Can be just a dummy transmission gate which is always on. Or putting a small resistor here. Effectively it is like that. I am putting a small resistor here. So this series R, which can be simply like a transmission gate, will avoid this problem. So one is NMOS, one is PMOS. Therefore this is connected to ground or VSS, and this is connected to VDD. So this is one of the solutions. Essentially, this is one thing that when you design, need to consider. Make a same delay from up and down till switches. Another point is, anyway, as we discussed last time, because this upward and down are fast signals, there will be, because of this parasitic capacitors, there will be clock fit through and VCTL. And there will be another phenomena which is charge injection, because here I have capacitors. So we will show how charge injection affects. So therefore, in addition, even if everything is ideal, of course, depends on the magnitude value of these C values, but practically anyway, we may have some small spikes on VCTL due to clock fit through and charge injection. Why it's not stable? You mean that during this time frequency will change? You know what happens? Practically it creates a phase offset. If it's this, but practically you will see a phase offset between input and output. Output of VCO and input frequency, input phase. In practice, that leads to that phase offset. Because of that phase offset, then it's after all, you know, the loop is locked. When loop is locked, what happens is in lock condition, it works in such a way, the average current which is given to VCO will be almost equal to 0. And this average current will be almost, the average charge in fact, will be 0 in the locking condition. So here there is a disturbance, so some charge is given and some charge is taken. During that time there is a change, a small change, but that is compensated with that phase error, so that it doesn't come to the picture. So that phase error will be sensed at the end. So in fact, if you look at this, this is like a signal. If you withdraw VCTL, it will be like this. Suppose it is a steady state, it will have this ripple, it will come back, it will have this ripple, it will come back, right? Therefore, your average VCTL now has changed. Right? Of course, it is practical, it's not like that because this width is very small. In fact, I should put this like, this is very large compared to this width. So there is a small change in VCTL, a very small change. This small change actually even will appear as an offset in the frequency. So there will be offset in the frequency, there will be offset in the phase. But it doesn't lead to instability, no. It will be still stable. Because you have a low-pass filter. Low-pass filter avoids instability. For example, the way you can model it, you can consider you have an ideal charge pump, you have an ideal phase frequency detector, means that delay from output of phase frequency detector to charge pump output is same from up and down path. But then this appears as a step disturbance to the input, right? Therefore, input of VCO will be this VCTL plus a step disturbance. Now, in the model you make it like this. This is VCTL. You add it with a step disturbance. This is 0 level. Okay. Now, these two are added and then this will go to VC. So, and okay, yeah. Other thing, for example, this charge sharing, how it happens. See, this is a current source. This is a switch. Again, this is a switch. And this is a current source. So any current source has a parasitic capacitance. Now look, suppose both switches are off, right? So this upper and down. Upper is 1 and down is 0. Therefore, these two capacitors will be discharged, and then effectively the voltage across these capacitors will be almost 0. Now, for a short time they will be on, right, in a steady state. Now when they are on in a steady state, what happens is, now suddenly you are connecting these two capacitors to this output voltage, right, and these two capacitors had 0 charge. Now they have to charge to the voltage. This was 0, means that this effectively has settled at VDD, this node has settled at ground, and this node has settled as VCTL. Now you switch on both of them when those narrow pulses are generated. Now at that time, this node and VCTL will get connected. And then these three voltages are different. So what happens? Then there will be a charge sharing, which will create a new value of CVCT. So this will be a problem. Of course, if value of C and C2 compared with this C par 1 and C par 2 are quite large, then this will be negligible. Otherwise, you will have a change in the value of VCTL just at the start of switching during that narrow pulses. So this is charge sharing effect. I actually wanted to give this as a quiz to you. So therefore you see how it works, how this charge sharing will change value of VCT. It's very simple, and consider switches are ideal. Okay, there is one important thing which is called jitter. Now we will discuss about jitter. So therefore, effectively this effect is not very considerable, but anyway, be cautious about this charge sharing. Okay, what is jitter? First of all, suppose we have a signal with a frequency constant omega 0, phase constant phi 0. Now suppose this is coming from a VCO, and then this VCO operates in such a way, anyway it's in a practical environment. Therefore temperature, for example, one of the environmental parameters changes. Due to change in the temperature, what happens? Omega 0 changes, right? And temperature drift, is a very slow process, right? Therefore you have a very slow variation of temperature with time. So how does it affect on VCO? Therefore, effectively your omega 0 won't be omega 0. So it will be a delta omega 0. And this itself is a function of time. So even this is not a constant value. It changes with time. So therefore, effectively this will be a function of time, but it can be a very low frequency function of time. So how do we model it? We say that xt has frequency of omega 0 with a phase which is a function of time. Now, it is not limited to this. Suppose you have transistors and all MOS transistors have flicker noise. And flicker noise is a low frequency noise. Flicker noise can change the bias point of transistor, simply, right? Therefore, the effective current you get from a transistor, a DC current, is not constant. Actually, due to flicker noise, it changes again with time very slowly. But this time, in contrast to temperature, it's not a predictable value. It's not a deterministic value. So because of flicker noise, therefore, we have a random variation but low frequency variation with respect to time. Due to temperature, we have a deterministic variation. In general, we call it VNT. Means that whatever variation we have, we include it in one phase which is changing with time, whether it is deterministic or it is not, and we call it phase noise. And this phase noise actually means the noise which is added to the phase. Okay, it is deterministic or it may not be. And this is actually what is called jitter. In fact, jitter and phase noise both have originating from same concept. What is that concept? Is that if you have a signal, for example, a square wave, if you look at it at different time stamps, the effective frequency you see will be different. How this happens? If you, for example, look at an oscilloscope, sampling oscilloscope, you sample it at different times. So what you will observe on the oscilloscope will be something like this. You will see this is blurry. This edge is blurry. This is because frequency or effectively phase of this signal is changing with time. So this is called jitter. So this exists in the PLL also. So VCO has its own jitter. Even if you consider reference signal, which is input, doesn't have any jitter, it's ideal. But VCO has its own internal jitter because of sources of noise and temperature drift and other things. So how PLL responds to this jitter? What will be the effect of this jitter in a PLL? So we go with the charge pump model of PLL and then we'll look at what will be the effect of jitter in PLL. Okay, so this is a simple model of charge pump based PLL with 1 0. Okay, so there are two sources of jitter. One will be jitter which is coming from input. It may or may not be present, depends on the accuracy of input. And the second one, jitter, which is coming from VCO. So how these two will affect operation? So first of all, what will be the transfer function? So transfer function what was the transfer function? Last time we derived it. It is a low pass transfer function, right? Therefore, phi out 1 upon. So it was some constant into RCS plus 1 s square plus 2 zeta omega n s plus omega n square. Now suppose it has jitter, right? And jitter simply can be modeled as a noise which is added to the input. So I call it PNS. Therefore, if there is a jitter at input and that jitter is too low, means that it is very low. So essentially this phi n is a part of phi n. See, because these two are both adding to the input, therefore this phi n is a part of phi n. So transfer function for jitter at the input will be same as transfer function of PLL loop, which is a low pass transfer function. Therefore high frequency jitter automatically will get attenuated by PLL. So that is a good thing, because this means that automatically PLL behaves like a filter for high frequency jitter. But for low frequency jitter, very low frequency jitter, this transfer function means that it is bringing the jitter into the entire loop, because this low pass filter will pass it on. Now, if we have noise due to VCO, then it will be modeled as a noise which will be added where? Where? It is phase noise. So it is not a voltage noise. So where I should add it? At 5 volt. Therefore, it will be added at the output of VCO. Output of VCO divided by S. It is the output phase. So I add it there. So here I put another, and then here there will be phi. Just we want to see that what will be the response of PLL loop to these two types of jitter. Now again, what we do for this, we consider phi in as 0. Here also, if in fact, because these two are same, I told you like transfer function is same as phi out upon phi in. But here, to see what is the effect of phi in, because now input is here, so I explicitly make phi in as equal to 0 to see what will be the effect of this jitter. So now loop will be like this. In fact, look at this as an input, okay, and this is feed forward and this is feedback loop. Therefore, this is loop gain. Due to VCO. See, this is P out. In fact, this is output. Right? I show it in this way. So what is the transfer function from input to output if there is no feedback? Now look, this will be like feedback. This is the entire loop. This is like feedback and this is feed forward path, right? To output. So from feed forward path to output, I have gain of 1. Right? And this is my feedback. Therefore, effectively gain will be feed forward gain divided 1 plus loop gain, which is same as before. So, loop gain is same as before. So, the transfer function will be 2 pi cs square, same as before. So it is s square plus 2 zeta omega n s plus omega n square. Now it's very interesting. This is a high pass transfer function. What does it mean? Means that if there is a high frequency jitter in VCO, actually it will come to the output. Therefore, PLL VCO should be designed with a low phase noise or low jitter. PLL is not able to omit that. In contrast, PLL is able to omit low frequency jitter of VCO. That's a very interesting behavior. If this is, for example, log omega, and this is the transfer function, So we have two types of transfer function. Okay, so then here I call P out upon P in as this is magnitude versus omega. In the first case, it was a low pass, right? So it was having something like this. And transfer characteristics was similar to transfer characteristic of filter, closed loop PLL. Now here again it is similar, however, now it is a high pass transfer function. Therefore, this now will be a corner of high pass transfer function. I show it by that. So what does it mean? Means that if we want to get rid of this problem, if we have to shift cutoff frequency of filter to the right? Or essentially closed loop performance of PLL should be in such a way cutoff frequency should increase so that we would be able to attenuate jitter of VCO. But at the same time, by this work, we are doing two things. First of all, of course, low frequency noise jitter from reference will come. That is one thing. And second thing, as you know, we didn't want this bandwidth of this filter to be very high, right? We want to limit it so that we should be able to get proper locking, right? So this is again the same conflict that we have. So this is one important thing. And actually, then we will see even it is not limited to this. There will be other problems also. So loop bandwidth should be optimized. So essentially this means that, see, after all, this means that the whole point in design of PLL is loop bandwidth. It should be optimized very well. And there is one more point here. This is not only a matter of this. If you look here, poles will be imaginary, right? What will be root locus of this? I will just plot it. Because I am showing this high pass filter in this way. But actually this high pass filter won't be as simple as this. Means it won't be flat here. Even it will show some peaking, right? Suppose your zeta is less than 1. The whole low pass filter will show peaking. And then if it shows peaking, then actually you will have something like this. This high pass filters. And eventually even low pass filter also will have some peaking. Right? Therefore this is something which is called peaking in jitter. Means that not only it passes but also it amplifies jitter. Right? Therefore this is very important to see what will be this value of zeta eventually, which determines the amount of peaking, which also will determine jitter peaking. And therefore, usually when you design a PLL, always, in fact, this is one of the things we do. We always look at what will be this jitter peaking performance. We have to simulate that and then make sure that phase noise that we get will be below some value. So I don't go into the details of these designs. That is enough to understand it. But then the detailed design will go with, like, for example, if you want design. So now there are two things. Do you want to design for some application like analog or RF, or do you want to design for application like digital? So these two again will be different. And the way that we have to look at this jitter will be different. And one more thing here. Yeah, here I showed you. One more thing here. Here if you look, we have a 0 also. So if you look at the phase which is coming from input here, because of 0, actually we have one peaking because of this. We have one more thing here also because of 0. Now what will be the relative position of these poles and this 0 depends on the value of zeta and essentially looking. For that, just I will show you what is the root look as, just for information. If you remember, we had 2 poles at 0, right? When there was no compensation for type 2 and charge bomb was type 2. Now how poles will change? You are familiar with root lookers, right? You know what is root. And this is 0, which is minus 1 upon RC. Right? RC is this RC. See, I am looking at how location of these poles will change according to the gain in the loop. Gain in the loop is KVCO into I upon 2 pi. According to that, how this position of poles will change. If you remember, it was a function of KVCO and I upon 2 pi. So we will have 2 imaginary poles. So this is the direction we increase the gain. So this is the direction, in fact, zeta increases. See, zeta increases in this direction. Zeta is minimum here and then it increases. Therefore, poles are at the beginning imaginary and then they will be real. This is the 0, which is minus 1 upon RC. So it can be shown. It is essentially a circle with a center of minus 1 upon RC and then we are changing just value of K, which is the entire gain of loop. Now by increasing K, as K increases, how this changes. In this particular case, K will be this value. KVCO multiplied by I upon 2 pi. So now what will be the transfer function of the system? Anyway, it has a 0 at minus 1 upon RC. And position of poles are like this. Now there are 2 cases. Either poles are imaginary or poles are real. And in case poles are real, in case poles are imaginary, we start from here. Therefore, this will show some peaking. It can show some peaking. We had also 1 0. But, however, if you notice, at least up to this point, real part of this poles is before 0. Right? Therefore, if I plot the transfer function, at the beginning, when K is small, and this is for small k. For a small k, real part of poles, absolute value of real part of poles will be less than 1 upon RC. Right? We are here at the beginning, we are starting from origin. Because this condition is valid, therefore we will see effect of poles first. Therefore, transfer function actually will reduce. And then it will be flat because of 0. right? Not flat, actually it won't be completely flat because this is second order. Therefore, effectively actually here, because this is second order, we have 2 poles and then we have 1 0. So effectively here we'll have more slope and then it will have less slope. And of course here, because the toe is small, we may have some picking, right? Therefore it may behave like this. No 2 picking. Now if we increase k, means that now poles will come on the left side of minus 1 upon RC and still they are imaginary. Then this picking will reduce, but now 0 effect will come to the picture because now 0 will appear first. Therefore, at low frequencies, first we will see effect of 0, right? And then we will see effect of poles. Sorry. Lock on. And same, here it is, right? Okay, so that is in fact one of the worst cases. Look, here it is, here k was small. So this is related to this plot. And this plot is for the case absolute value of real part of poles will be greater than 1 upon RC. Therefore, first we will see effect of 0. And then here you see you have a picking. And this picking actually will increase jitter. Therefore, loop will behave as an amplifier for VCO jitter. That is a very important thing. We prefer to have this without any picking. No? So still here poles are imaginary. And then when we reach here, means that now we are increasing damping factor, right? When poles are completely real. Now one of the poles still here and here also. Still poles anyway are in the left side of 1 upon RC. Therefore effect of this 0 will be always first. So this will be the better design with respect to stability, but worse design with respect to jitter. Therefore, again, this everything comes for how we assume value of zeta. After all, it's an optimization. Because here your zeta is higher, right? Even if you go under this case, like you have just 2 real poles, your loop will be slower, but then it's completely stable compared to this. Because here your poles are, being close to this real first case when you had your close. Yeah, settling time will increase. Settling time will increase. Of course, settling time will completely, imaginary pole also is very high. In fact, it is infinite. But system also is unstable. Here, there is a optimum case for settling time because system will be either underdamped, critically damped, and overdamped. When it is underdamped, it is slow. When it is critically damped, it is better. And then when it is overdamped, it will be faster. But if you just increase it too much, then actually it will become slower because it will take time for this ringing to settle. And in PLL, actually, we are interested to settling, not just rise time or fall time. So, therefore, effectively, system is not completely fast even if it is overdamped. So, the oscillation itself will take time to settle. And unless it has not settled because of this oscillation, we will see different frequencies in the loop. as we discussed, right? Because it is oscillating, therefore voltage goes up and down, VCTL, therefore frequency changes, therefore effectively we don't see a periodic waveform until it settles. So, but with respect to stability, this is anyway is better when 0 comes left side. However, it is worse for jitter performance. So this is one thing which is very important in the design. Well, actually one increases, one reduces. There won't be any picking, yes, there won't be. Yeah, it's just delay, nothing else. But yeah, yes. No, see, if you make both poles real, for example, one pole will be here now. I show it by this symbol. One pole, for example, will be here. And 1, 0. No, it will be good because you don't have picking anymore. Effectively, this pole goes to left, right? Therefore, effectively, this pole will be the dominant pole. So you have one pole, 1, 0, and pole is on the left. Therefore, first you will see effect of, anyway, you will see effect of 0 first. Okay, yeah, his point is that we will see effect of 0 first. Anyway, this picking will be there. But therefore, this is not good with respect to jitter performance. It is good with respect to stability. Here, if you don't have as such a large picking in the left part, when your loop gain is small, it's not very large, here you won't see any picking. And with respect to jitter performance, you have better design, but with respect to stability, you have to be careful. The reason is because, as I said, the stability also itself is a problem. Because see, this is very interesting because this charge pump is a discrete system, right? As I showed you last time, what was the transfer function? 1 minus e to the power minus st, right? T is the sampling frequency cycle upon s, right? This was the coefficient of that sampling. It was the transfer function of sampling system. So suppose f is small, okay? So this can be approximated by 1 minus 1. This will be plus, right? St upon s. So no, in that case actually won't be, but if you just continue, for example, s square, t square. Okay, minus. Right? What happens is this itself will create, this is like a transfer function, right? Now you just omit s, it will be 1, t, I think this also was ts. Will be 1 minus st, right? This itself adds to the phase, right? This adds some extra negative phase to the phase shift because we had considered everything is continuous time. Therefore, we had just 1, 0 and 2 poles, right? But effectively, this charge pump is not like this. It has some extra phase shift due to this effect, sampling effect. Therefore, that's why when we design, we have to be careful about choosing this bandwidth. Bandwidth of this filter, phase margin of this filter. So, phase margin should be chosen at a very high value. Okay, so now for example, if I want to decide, now suppose I want to design. Yes, what is the question? Yes, it will have. It will have. What he says is that because ST is small in fact, therefore effect on phase will be more than effect on amplitude. But it will have, if you remember in the sampling part, there is effectively this effect is a what is called the sink function. Therefore, at very low frequencies, it will be almost 1. But as frequency increases, it will even attenuate the amplitude. So effectively, what does it mean? Means that if I want to choose bandwidth of this filter, because it's with respect to VCO, jitter, it is a high pass transfer function. Therefore, I have to choose bandwidth of this filter properly. At the same time, for input jitter and for locking performance, I want to choose a low bandwidth. Therefore, there is an optimization. Okay, so this was some of the non-idealities in PLL loop. So therefore, if I want to design, so filter, see, first of all, one is VCO, one is filter, right? These two are more filter actually means the entire thing, means that pulse frequency detector plus charge pump. This is of course straightforward, but we are talking about charge pump and VCO. So see, you have a loop, right? And suppose you have a divider in the loop also. So then this will be completely this pulse frequency detector and charge pump. Then this is VCO. So suppose we are talking now about frequencies, okay? So suppose F in has a range, okay? And here's I have a divider. Divider is linear component, therefore doesn't matter if I put it after frequency and then integrate or vice versa. This is just a divide by n. Of course, we have frequency scalar also and this thing. So right now, just this is a simple digital PLL. So I put a counter, for example, here. I will get 1 upon n. So input frequency has a range. I want at that range this loop to lock, right, and operate properly. Therefore, VCO should be able. So F VCO should change between F n into F in 1 and into F in 2. So this is very obvious, trivial. So what determines my frequency range is just, range of VCO is just input frequency range. This doesn't have anything to do with this filter design. And therefore, effectively, I should have a very high speed VCO. Therefore, I can keep, for example, my center frequency of VCO if I have almost a completely linear VCO. I can keep center frequency and the average of these two and then design this VCO. Because then now I know exactly what should be the performance of my VCO. Because now F out will be center frequency plus KVCO VCTL. Even I can choose range of VCTL, therefore, according to the VCO I'm designing. Say, for example, that current start inverter, which will be the component of ring oscillator. So for that, I have a range of voltages, and accordingly, effectively, I get this VCO, and VCTL is input. So this, in fact, F0 is average of these two, therefore this will give me delta F, which will be the bandwidth I have around this center frequency, Fin1 plus Fin2 upon 2. So this is one of the things that I will look, and then accordingly I will design my VCO. But when it comes to the loop stability, loop bandwidth and jitter performance, then I will look at charge pump and pulse frequency detector. So therefore, for example, if I want to design a PLL which is able to use, for example, divide by 16 and generate a 1 gigahertz frequency here, then generate, for example, from 1 gigahertz to 2 gigahertz, then means that I will know what is my input frequencies. This is 1 upon 16, so this range will be 1 gigahertz to 2 gigahertz, and then input frequency accordingly will be defined. So this is not a big deal. The main part is how to decide about filter. Oh, you mean capture time? Locking time will be determined by the bandwidth of filter, right? That itself again depends on the bandwidth of filter. No, overall it will depend my loop gain. See, after all, it will depend on my zeta omega n. Zeta omega n is a function of my loop gain and filter cutoff frequency, right? So inherently it's there. For example, even in this case, charge pump, what was the relation for zeta? It was a function of KVCO last time we had. Yes. Here relation was reverse, of course. Of course, see, there is one more thing also. It's not only KVCO, because see, suppose you cannot, anyway you are designing, for example, a current starved inverter. Therefore, input voltage range will be something between threshold voltage of a transistor and your VDD value. So your VCTL anyway cannot be something other than this. Unless you put another circuit, for example, like attenuator or amplifier, and usually in digital design nobody prefers to do all these things, add an analog component. So that range also is known. And your frequency range also depends on the design specification. You want to design a VCO with a range of 1 gigahertz to 2 gigahertz. I mean, practically you want to use it. You may want to design it from 0 to 2 gigahertz, practically. But suppose if this is the range, 1 gigahertz to 2 gigahertz, that is given to you. That also affects on your KVCO, right? Because it's a current starved inverter. Therefore, your KVCO is a function of that current source that you are putting there. Okay. Then it will be a sine wave generator. So even if you don't use current starved inverter, you use something else. Anyway, you need some controllable delay component. Anyway, it will be a function that will define for you what should be the KVCO. What I'm saying is that you don't consider KVCO only is affecting zeta omega n, or KVCO is only affecting frequency. However, when I design, I look at my loop for stability and jitter performance, loop bandwidth, and I look at my VCO as a frequency provider. Then I write my equations, and then I will see now how I should play with these values to get the best of all. See, for example, here my RC will determine location of my 0, right? My KVCO will determine omega n. My zeta omega n actually will be determined by R into KVCO into I. Forget about power right now, right? Therefore, zeta omega n actually is determined by 3 parameters. So I have freedom till now. I have location of 0, which is RC. So see, I have 5 parameters. R, C, 4. or C KVCOI. How many constraints till now I have? I have 2. Location of 0, value of zeta omega till now. So still I have enough freedom. Now I come back to the VCO. That also will add 1 constraint. Now I have 3 constraints and 4 values. So still 3 constraints, 4 values. That is also good. And then I can see if anything else can limit my performance. Otherwise, then I will try to add power. Therefore, I will have 4 constraints, 4 parameters. Then it will be designed. Means that then it will have only 1 solution. See, the point is here, actually speed here will be proportional to 1 upon zeta omega. Therefore, this means that if I increase my KVCO, it will be good. Now, if KVCO is not high for n number of reasons, it is low, then I can compensate it by increasing power, right? Still, I can get same speed. Means that though my VCO is slow, but because charge pump now is charging the capacitor quickly, I compensate the speed at that feed-forward path. And this is just the rule of thumb. It's not a very instruction for the design, but always usually what we do is that we choose cutoff frequency of this loop filter, okay, at the end. Means that when I have a closed loop filter, see, after all, VCO is like a filter, right? Transfer function is a low pass filter. I look at this as a low pass filter, and I will choose in such a way this low pass filter so this is log omega, this is phase transfer function or omega frequency, both will be same. So if I have a 0 and suppose I am in the case that 0 is after pole, okay, so in that case and my picking is very low, therefore I will have something similar to this. So this is called crossover frequency. Means that when I will get almost the 0 gain out of this loop, right, the entire transfer function. Usually this is chosen to be, this we want not to be very large, right? We want to limit this frequency. Usually this is chosen almost around 1/10 of input frequency. Suppose if you have an input frequency of, say for example, this is divider of 16, therefore 1 gigahertz. 1 gigahertz upon 16 will be how much? 125 megahertz will be 1 upon 8. So it will be 60 megahertz. Suppose it's around 60 megahertz. 1/10 of 60 megahertz will be 6 megahertz, right? Therefore, definitely this should be below that. Of course, this is megahertz. Usually it's a large range. Usually input frequency is in the range of kilohertz if it is coming from a crystal. Megahertz is very difficult to develop. But anyway, so this means that it should be 1/10 of that. And then now you design the filter in such a way. Now you know this is the crossover frequency you want. Now you decide about location of pole, decide about zeta, right? This is all now, it's an iterative thing. So this is in fact the main rule of thumb for the design. And it looks actually very easy, right? But practically now really we should see like how really this loop is able to lock. That is one of the main things. So just I give you one. Just give me 5 minutes because I want to finish this today. See, just as an approximation to see how to consider capture range and lock range in the design. Just as an approximation. Okay, so suppose we have a loop. So coming back to the same charge pump. And this loop we want to lock. Okay, and just show you the blood filter. Okay, forget about these noise sources, just this is the loop, okay. So, what this loop does, essentially generates some low frequency voltage, or essentially if you consider DC, which will be this control voltage, and then will generate the frequency. So, but what is the maximum phase difference I can have at the input, right? The maximum phase difference that anybody can generate means delta phi. Okay. This always will be between these two values, right? So, therefore, I have a limited value for the delta phi at the input, right? At the same time, I am giving this delta phi to the filter, and I am extracting that DC component of this. Suppose if I have a delta phi, it's a DC value also, and therefore it is given to that filter, right? Effectively, that filter at low frequencies, which has this transfer function, it has some gain, like finally this PLL, or not this PLL, sorry, I have to say this. This actually will have some gain, right? At a DC, if I give a DC, I will get something here. In the case of charge pump, actually it will be infinite, right? So, but after all, whatever I get, if I apply a delta phi in this range, when it settles, response to this delta phi, it cannot go indefinitely to a large value as we discussed, because anyway there will be a limitation. For example, VCO cannot respond to voltage values above some value, right? VCO also has its own range. So VCO can generate frequencies however, this VCTL has a range. So it has a Vmin range and a Vmax range. After that, it won't respond to the variations, right? Variation in the phase. So if I consider this, so how much this can change? Suppose I have a VCO. What is the maximum change in the frequency of VCO? And suppose it is symmetric both sides. So I will put, for example, suppose I just deduct, say this VCTL. Suppose I deduct some value of DC from this, so that now I will have this VCTL mu. Okay. So that this will be just an AC value, okay, just removing DC. Therefore, for simplicity, I can say that delta omega VCO will be just this K VCO into VCTL. Okay, so this is the original VCTL. Just I have removed DC part, make it AC to show that, okay, it is changing, it is symmetric. So this is center frequency. Frequency can increase or can reduce. So I just show it in this way. So see, this is also the maximum value of variation in the frequency of VCO. It cannot answer or generate more than this. Means that the maximum variation it can generate around omega 0 is this value, either in positive direction or negative direction. This is also the maximum phase difference that I can generate. 4 pi is same as 2 pi. Therefore, effectively, I have inherently limitation on the values. Okay. So therefore, if I have a loop and it is locked, I want to keep it locked, then means that this constraint should be satisfied. Means that the frequency change should be in such a way, always it should be within this window. Within this window. Okay? And then I will have VCTL as a function of, VCTL is a function of, VCTL, essentially the value of VCTL that I can generate is a function of charge pump, right? I can write VCTL, for example, on phi in. This also will have a transfer function, right? This is a transfer function. Again, it was a second order transfer function. So, what is the maximum change in VCTL I can generate? It depends on charge pump. So, suppose the maximum change in the VCTL also I can generate due to this delta phi if I change the input frequency, not phase. If I change input frequency, PLL also now will go to a new frequency with a second order system response. Now when it goes to this new frequency, this means that this VCTL now will go from VCTL1 to VCTL2. But what is this maximum difference? This depends on how charge pump changes this. So I consider this delta VCTL due to change in my input frequency can maximum go into this range, Vmin and Vmax. Therefore, what does it mean? Means that I consider actually this is your lock range, right? Lock range actually is the range at which this VCO can operate. So, if this is my lock range, what does it mean? Means that, so this VCTL, so delta omega VCO will be plus minus KVCO into some coefficient, I call it KP, into my inherent phase shift, which will be some 2 pi or plus minus 2 pi. Means that effectively this will be an estimation of lock range. Now the question is, what is value of Kp for the charge pump? You derive it. Okay, this might be also, next week we will have again a quiz. This might be also a question. Okay, so this is just a rough idea of see, this is the best lock range that I can get, right? Around omega 0. This is the best lock range we can achieve. This is the best lock range we can achieve. Now the question is, what is capture range? So here I had assumed that, okay, VCO is working properly, it will changing its frequency with the VCTL. But when loop is not locked, VCO doesn't operate in this way. What VCO does? VCO is operating at its free running frequency on average. Now, how we can estimate? So now this is just an estimation. And then it will give one idea of what will be the capture range. When loop is not locked, so I have a phase detector, phase frequency. Essentially, all phase frequency detectors are some sort of multipliers. So you assume you have a multiplier now, right? And you have an input frequency. We have a square wave, but to make analysis simple, just assume first harmonic of that square wave. Okay? Therefore, I have some omega in, and loop is not locked. Okay? So, VCO. So, omega VCO will be omega 0. So, this is for capture range. Therefore, loop is not locked. Now, what will happen? Loop is not locked, but anyway, it's working. I have a frequency of omega in. At the input of phase frequency detector, I have another frequency. What is that second frequency value? Yes? Yes? Free running frequency, exactly. So you are giving two frequencies to a multiplier. Simple. So therefore at the output, you will get two terms. Right? Sine or cosine doesn't matter. So you will get omega in minus omega 0. You will get omega in plus omega 0. Okay, this is output of pulse frequency detector. Now this is given to the charge pump. Charge pump is essentially a low pass filter, and therefore it will attenuate both of them. First of all, suppose this will be attenuated in such a way it is almost negligible. Therefore, I don't care about this term. What is important is this term, right? So now this term comes to the low pass filter. So now low pass filter will attenuate this, like it will be a low pass filter. So what will be the output of this? So it is just, I have now a new frequency, right? Therefore now, output of low pass filter, in the case I have omega in minus omega 0, it's a filter, right? Therefore, it is just enough. This is not, of course, so it's a low pass filter, right? Anyway, for example, it has 2 zeros, 1 0, 2 pole, right? So this is the characteristic, right? Log omega. This is magnitude of H charge point. So it's something like that. So therefore it will start attenuating. So whatever it has, okay, whatever transfer function it has, after all, what I will get at the output of this, which will be in fact now this VCTL, it will depend what I am getting from that effective low pass filter. Yes? What is question? This is multiplier. I assumed I have a multiplier. That parts frequency detector is almost a multiplier. Effectively, it generates these harmonics. Even it can generate like 2 omega in plus omega 0 and this. So this is just a simple assumption. So anyway, whatever performance it shows, do you agree with me? Like when it was locked, effectively I had a DC component. Here I have a component above DC. Therefore, effectively what I get here will be less than what I would get if I had just a DC component, right? Effectively. No, that is fine. The reason I'm not talking about that, because mostly we are talking about digital PLL. But actually, in many applications, people use active RC. But that is fine. I mean, it doesn't change anything. It's just, it adds a gain to the filter. Charge pump gets 2 inputs. No, that is fine. You can consider, for example, up minus down, right? What is your question? Yeah, see, up is a function of 2 input frequencies. Down also is a function. Usually, if you look at up minus down, that will give you an idea, function of input frequency as well as phase. So, what is your question? This is effectively what we are doing. See, that 2D flip-flop are modeled by a multiplier. And then that multiplier output is given to charge pump. And instead of the charge pump, we consider we have a low pass filter. So this is just for simplification. So coming back to the original analog PLL. So we have just a multiplier, we have just a low pass filter. Okay. Anyway, that low pass filter will have a lower gain when I have a frequency above 0. Compared to the case I have a frequency equal to 0. Therefore, in this case, the amount of voltage that is generated in the unlocking case is less than the voltage that is generated in the locking case. This is the only point that I want to emphasize. That this value, now this VCTL for unlocked condition will be less than what I get if it is locked. Because in unlocked condition, even in a steady state, the input will be always a frequency which is above 0. So that is just enough, this is just a very rough and then just a very rough model, but this is the conceptually how we can estimate what should be lock range, what should be capture range. So now I am getting a smaller value, okay, so because it is attenuated due to filter. Now low pass filter will attenuate it, whatever I get now will be less. So therefore, the maximum here, the maximum value I can get again will be, if I consider I have 2 pi phase difference, therefore I will get the maximum. Now this voltage is getting applied to VCO. For VCO to be able to lock, right? When this is applied to VCO, this should be, see, VCO, omega VCO is omega 0 plus minus K VCO plus K VCO VCTL. VCTL can have negative, positive value. I keep it here and consider VCTL is absolute value. So if we look at this absolute value of this K VCTL, this VCTL which is generated, now VCTL unlock is applied to VCO. If this VCTL unlock, so what is effectively maximum VCTL I can have, VCTL max for VCO is omega VCO minus omega 0 upon K VCO, right? Considering positive value, negative value will be omega 0 minus omega VCO. So this is the maximum voltage which can be applied at the input, so that, and then I will get this omega VCO. Now I have a frequency which is omega in. I want PLL to be able to answer to this omega in, right? Therefore, this omega in should be less than omega VCO. Then this means that this VCTL that I am getting see, I want VCO to respond to this VCTL. Maximum VCTL I can apply to VCO is this value. Now, for the PLL to be able to answer to this value, this actually should be, no, what should happen is, see, this VCTL that I am getting in unlock condition